I want to show you one of the most powerful ideas in all of modern science. And we're going to start with a simple game. A game you can play right now. But I gotta warn you, you almost certainly can't win. Not if you're playing against a quantum computer.
So the game is super simple. It's you versus a computer. All you have to do is make a coin land on tails. Sounds easy enough, right?
Okay, here are the rules. There are 3 moves, and they're all secret. First, the computer makes a move. Then it's your turn. And finally, the computer gets one last move. So, the big question is, what do you think your odds of winning are? Well, if you play against a regular, classical computer, it's exactly what you'd expect. A 50-50 shot. A coin toss. But when this exact same game was played on a real quantum computer, oh boy, the player's win rate just falls off a cliff. The computer won almost every single time. And get this, the only games it lost were because of its own errors. So what is going on here? How is that even possible? It's not cheating, it's not magic, it's quantum physics. And if we can understand how the computer pulled this off, we'll see exactly why this technology is such a game changer.
Okay, to get how it won, we first need to wrap our heads around what a quantum computer actually is. Because it is not just a faster version of the laptop or phone you're watching this on, it's something else entirely.
You know, there's this fantastic analogy for this. You can't invent a light bulb by just making better and better candles. A light bulb is a fundamentally different piece of tech born from a totally new understanding of science. While a quantum computer, that's the light bulb.
The huge difference, really, it all comes down to how they store information. Your computer uses bits. Think of them like little light switches. They can either be on or off, a 1 or a 0. That's it. But quantum computers use qubits, and this is where things get wild. A qubit can be a 1, it can be a 0, or it can be in this weird fluid combination of both states at the exact same time.
And that ability, that whole being in multiple states at once thing, that's a core idea in quantum mechanics, and it's the secret sauce. It's the key to solving the mystery of our impossible coin game.
The technical term for this is superposition. It's a property that lets a quantum computer explore a mind-boggling number of possibilities all at once, giving it a kind of processing power that normal computers just can't even dream of. Here's a way to picture it. Imagine you flip a coin. While it's up there spinning in the air, before it actually lands, is it heads or tails? It's kind of both, right? It's in a state of possibility. Well, that's what a qubit does. It exists in that spinning state, holding the potential of both 1 and 0 simultaneously. So let's go back to the game. On its first move, the quantum computer didn't flip the coin to heads or tails. Instead, it put the coin into a perfect superposition, that perfect spin between both states. Now here's the kicker. When it was your turn, it didn't matter what you did. Flip it, don't flip it. You couldn't break that perfect quantum spin. Then, for its final move, the computer just did the exact reverse operation, perfectly unspinning the coin right back to where it started. Heads, a guaranteed win every time. But believe it or not, superposition is only half the story. The real magic, the truly mind-blowing power of a quantum computer gets unlocked when you start linking these qubits together. That's when their power just goes off the charts. This link is called entanglement. It's a connection so bizarre, so frankly weird, that Albert Einstein famously called it spooky action at a distance. Basically, what happens to one entangled qubit instantly, and I mean instantly, affects the other, even if they're on opposite sides of the universe. You see, entangled qubits stop acting like individuals. They behave as one single interconnected system. And this means, well, get this, every single time you add just one more qubit to the system, you can effectively double its total processing power. That's not adding power, that's multiplying it. We're talking about exponential growth. So, okay, why does all this quantum weirdness actually matter to you and me? Well, because harnessing these strange properties isn't just for winning coin games. It could give us the keys to solving some of the biggest, most complex problems humanity has ever faced. Let's talk about security. Quantum uncertainty lets you create encryption keys that are physically impossible to copy. Imagine this. The second a hacker tries to even look at the key, the very laws of physics force it to change, which instantly reveals they're there. This isn't just theory. Major banks are already testing systems like this. Or how about healthcare? Simulating complex molecules, like the ones in our bodies, is a huge challenge for even the world's best supercomputers. But a quantum computer could do it perfectly.
This would let us design brand new drugs and find treatments for diseases like Alzheimer's at a speed we can't even imagine right now.
And it could even power a future quantum internet. By using entanglement, it might actually be possible to teleport information from one place to another without physically sending it. A network that's faster and more secure than anything that exists today.
But at the end of the day, this isn't just about building faster machines. I love this quote from the physicist Shohini Ghosh. She says, "Quantum computers are a way for us to probe the mysteries of nature. They're a whole new kind of tool for understanding the universe itself."
So by embracing all this weirdness, this strange, fluid, uncertain nature of the quantum world, we're not just building a better computer, we're opening a door to a completely new reality of discovery. And in a universe that's built on uncertainty, well, that's what makes the future so incredibly exciting.